I come from a team of mathematicians, engineers, chemical engineers, very few chemists, so we're very diverse in the team, and so we just help each other a lot. So if I'm lacking in maths, which I am, I'll go straight to Aaron, or I'll go to another work colleague. So between us all, we seem to be able to solve problems, but Aaron has taken a sidestep from maths a little bit, and he's working on a spin-out company from CSIRO. So he's a little bit distracted, and so if you guys can help with anything that we have, that would be really great. So I'll just present to you some of the work that we do in the group. We work on nanomaterials for industrial emissions control and resource purifications, but we're basically a group who makes nanomaterials, nanoporous materials being the operative word. We work in gas storage, so being able to store hydrogen, methane gases. We also work in using these materials as batteries as well. Our group is heavily based in membranes, so we make these materials and we incorporate them in membranes for nanofiltration, gas separations. We have all the facilities we need at CSIRO. We're lacking a little bit in manpower. We've got a few members who have managed to secure some overseas positions, so we're a bit struggling in that, but modelling and mathematics is something that we need with membranes for predictions. We also use them for agriculture. So these nanoporous materials, as you can see, are porous, so you're able to store gas molecules inside. So I've been working towards the agricultural sector where you can store fertilisers and then slowly release them. We also use them for catalysis, drug delivery, so you'll be able to store drugs and you can release them upon demand. Water quality, because they're porous, they can be used as a purification system, and a lot of our work now is targeted at triggered release materials. So it's good that you can store, but you need to work out, if you want to use it, how to release it. And that is something that Aaron hasn't really worked on, in the sense of the mathematical side of the releasing of the molecules or the stimuli that's required. So I'll tell you what some of the materials that we work on, and they're called porous aromatic frameworks. They consist of metal ions covalent, inorganically attached to organic linkers, so you've got ionic interactions happening. They're generally crystalline, sometimes they're amorphous, but that doesn't really make it too much of a difference, providing that they form a network system, and so that network system is where your porosity comes from. They can be from 5 to 100 nanometers in size. We also work with polyhedra, so they're smaller, infinite little cages instead of larger, discrete, big molecules, you could say. They're much smaller, they're also very crystalline, and they can also be soluble. So that's an advantage that they have over metal organic frameworks, but their porosity is very low. We also work with using organic porous systems. The porous aromatic frameworks, they are amorphous, and so modelling is essential for predicting their capacity for instance, storing gases, and also their structure. They're organic based, they have very porous systems. They could be the size of 2 football ovals if you were to unfold it and calculate the surface area within. They're very thermally and chemically stable, and they're also large in particle size. Material that we've just started to get out now are the hypercross-linked polymers, and so we don't have any modelling prediction in this area, and so that would be very useful to have for us. And they're much easier to manufacture than the porous aromatic frameworks. So that would be something that we would definitely be tailoring to go towards in terms of feasibility options. So a lot of the stuff we do with Aaron is virtual screening, so he can predict, well, he goes through a series of computational work to piece together some materials that we could use for a particular purpose. And so I'm not entirely familiar with what mathematical programs he uses, but he does a lot of DFT work, uses the Monte Carlo theory. So there's lots of things, and if you want more details, please contact Aaron for them. But what we do know is Aaron is essential to our team in the sense of being able to match experimental to computational work, and that's really important for even just publishing, but also going to industry and saying, hey, we can work on the simulation stuff, and then we can translate that straight into experimental. So some of the applications that we've got out of both simulations and experimental are for toxic gas removals. So canisters, being able to use the MOFs to be able to absorb any, well, not any, but selected toxic chemicals. Our team has worked out the capacity and their affinity for these toxic chemicals without, for instance, myself having to go test these. We use them for membranes, so filtration systems, and most importantly, we've actually used it for hydrogen storage for an alternative fuel to run cars. And we've had a project with the Defence Force based on Aaron's predictions as well as the synthetic side. But this is where we're actually going in towards, and where we do lack in any mathematical support. And that's having the materials being triggered by an external stimuli. So what you do capture, you can release and then reuse again. So we've noticed that it's quite important to be able to not only make something, use it once, but actually reuse it. So that's where we're wanting to be more fluid in our work, is that it needs to be able to be a full cycle. So we've worked with using light to release the gas molecules. So we've been able to capture CO2, and with a broadband UV, you can actually release the CO2 upon the exposure of light, and then once it's off, it recaptures it. So that's something that's quite useful in the power industry for flue gases, being able to capture carbon dioxide. We've also used magnetism to do the same thing, but with magnetism it can work in two ways. You can have it so you can isolate the material more readily, more easily than any other system, but it can also be used to increase the capacity, and it also can be used to release what you're storing. And in all cases, both two have been towards gases, CO2. And then we've incorporated both systems where you've got light and magnetism to do both things. So you can use the magnet to have a direct effect by increasing the gas capacity, but also being able to isolate it, and the light to be able to release the gas. And in both cases, they're both energy efficient, providing that your magnetism doesn't require too much energy to actually be put on. And so Aaron is located in the New Horizons building, level 3. I'm sure most people would know he has a lot of collaborations over at Monash, but he would be happy to chat with you after this if you had any questions that were more mathematically expressed than what I can give you.
Let's go back a few slides to that one when you had the 5 kind of panels.
Oh yeah.
Because I had conversations with Aaron about the maths involved, and I think maybe it's just worth mentioning, if I remember correctly. So that MOF candidates block there, my understanding is that there's quite a bit of uncertainty around what is the structure that's a potentially good candidate MOF to do what you want to do with, and that there's some graph theory and some other stuff involved in analysing the properties that successful candidates have. But there's also a huge, because the space is so huge.
There's an endless amount of building blocks.
So a huge number of candidates, and so there's a bit of a statistical design of experiments dimension to this, but also sort of graph theory dimension, a bit of optimisation, and also this idea that you might come up with the theoretical properties that a candidate needs to have, but whether that's buildable, whether you can actually make that.
So generally Aaron and I will sit down, so he'll ask me what's feasible. So I'll give him a list of properties, criteria that I need to be able to make it synthetically. Sometimes he comes up with these ridiculous molecules, and it's like, I can't make that, Aaron, it's impossible. And so
this balance between this huge search space and what the properties of success look like mathematically, and then whether you can actually synthetically create that. So it's a really interesting project, and I know there's already been some discussions with some students, but we're really after some academics who feel that they might have something to offer to supervision for students, and whose background might align with Aaron.
Yeah, that would be great actually.
It's very happy with this. This is about having to do molecular dynamics, simulation kind of stuff, and solving things to understand the properties of materials, or
yeah, I don't know what's the measure of success.
Is it truly geometric design kind of?
I think there's experimental data that says when there was this structure that had these properties that turned and these ones were not so good.
Yeah, so what we normally do is, for instance, with one of the defence projects, we go through what's in the literature. So we fish out, we look for particular pore sizes, particular metal ions, and so we do a lot of manual labour to start picking the ones out. And then he'll go through a process of, basically it's like is it a contour map or something, where you've got like a colour scheme where you've got pore sizes versus temperature, and so you find the maximum capacity. So initially for him to be able to do that, there's a lot of myself and then another chemist to say, all right, that's got a good pore capacity, but it's got a pore volume, and then so you try to match up the variables that work best. So if you want a high capacity at a high pressure, then you need larger pores, or if you want high capacity at lower pressures, you need smaller pores. So there's a lot of feeling, and then so I think it'd be good for Aaron to be able to get a system that we don't actually then have to.
Yeah. So I heard that as a black box optimization.
Yeah.
Constraints to do with practicality, whether something can actually be manufactured, of course it is synthesized. But yeah, I know there's certainly a dimension that kind of aspect to it.
Yeah.
You got 3 minutes.
Oh,
but we can stop.
I can. If there's any questions that I can answer, I'm happy to.
Great. Okay. So thanks to Kristina.
Oh, thanks. Oh, I do have a video. It's with membranes. I don't know if anyone's interested in membranes and being able to the interactions between the polymer and the additive that we add. I didn't go into it at all, but I'll just quickly, since I've got 3 minutes, I might as well do it. This is what Aaron started to work on when he first joined our team. Where am I here? Hopefully it works. Okay. Oh dear. So some of the problems that membranes have is, is aging, and aging is caused by polymers collapsing on each other. And so we've managed to overcome some of the difficulties with specific polymers that are industry related, where you can actually stop the collapsing and the polymer falling on each other. So you still allow the transport to happen, and retains its mechanical properties. It is not going to work, is it? No, it's not going to work. Whoa. There we go, sorry. So basically, yeah, the polymer chains undergo physical aging by the movement and the collapsing. And so what we want to do is, as I said, the porous aromatic framework has been really successful for us, and what it does is it embeds itself in between the polymers quite well. And the porous aromatic framework has, it is literally just aromatic systems. And so it wedges itself in between these polymer chains, and so, but it still allows the polymer to gently relax on itself, but without it diminishing the transport channels. But it also provides selectivity for the gases, so you improve, what you want to do is eventually improve the selectivity of the gas that you're trying to separate with these membranes. And so what the whole idea is that you kind of like have a membrane system that lasts longer. And that's what industry really want, is to have a material that they don't have to replace all the time. And so it would be really good if we could do some modelling around these porous aromatic systems with different polymer chains. So that's something that would be good.